calculation one, okay? So you're going to work on that. So how many of you have already looked at it? One or two, or nobody? Okay. So you can all open this file in your own browser or editor, whatever it is you have. Okay, now let's see, how does this work? Let's make this font slightly bigger. Let's just tell me when you can actually see it. Mono. Does this look big enough for you?
Yeah.
Okay. Oops, no, too big. Yeah, that should be big enough. Yeah. Come on. Okay, that's maybe too big. Okay. So what do we have here? Let's start from the skeleton of the code. What do we want to do? We have a bunch of predictions, okay, for rain by a bunch of weather stations, right? That was the problem. So have weather station 1, let's say it's CNN, and weather station 2, I don't know, it's AccuWeather, and the other one is, I don't know, why or what. So there are a bunch of stations, and then for every day, right, they give you a probability for rain. Okay, the first one gives you 0.1, 0.4, and the other gives you 0.7, right? Okay, so you assume that there is one station which is the right one, and you start with what we call your initial belief about every station. Okay, so a station can be new, so any one of these news is a station. So you can take the value CNN or AccuWeather or this one, and then let's say that initially just 1/3 for all the stations. Okay, now you observe it's raining or not. Okay, if it does rain, yes, then what we want to do is to calculate the posterior for this one, and we just define this to be the probability of this one according to our original prior times given the new data, okay, and the data is x1. So in general, we just say that xt is the probability of the stations given the data until that point in time. So in the beginning, you have no data, so it's defined like this. Okay. So this one we know by Bayes' theorem that we can just write like this: the probability of this happening, yeah, given the past. So this station doesn't have any past yet, so just x1 times the probability of the station. Okay, divided by the probability of the other stations. The same thing. I'm gonna write it down. So for every station, you look at the probability for rain, right? Okay, so why don't we go through it? So let's say for the first station, right? It gives us a probability for rain at 0.1. Yeah? So what should this term here be? Anybody? For CNN, well, when mu is equal to CNN, then what is this value? Yeah.
1/3 times 0.1.
Right. Yeah. So this is
Yeah. So that
0.1
0.1
and then
times
1/3. Right.
1/3.
Fine. And then this is the sum for every station, right? So that means we have the same thing here. 1/3. And then for the second station, 0.4, right? And then the third station, okay. So in this case, because everything is equal initially, then this 1/3 goes away. So it's, you can calculate the fraction and you get some value. Then you repeat the same thing for every station. You basically plug in this value. For each one of them, you get 0.1, 0.4, 0.7, right? And then basically, the posterior should be proportional to these numbers because they were all equal originally. Okay. So now we would like to do this with a code. Okay. But before we do this with a code, think about it. This same thing works for any time t. So if we say that this is just this thing, we already showed before that this is basically the same as writing so there are two ways to calculate the posterior distribution. One way is to look at the previous posterior, okay, and update it just based on the new observation. So this is what we do here. So this is exactly the same as here, okay. Or we can just say we look at all the data at the same time and calculate the posterior based on all the data. Okay. So these two things are equal. Oh, I forgot something here. Sorry, it doesn't quite fit. I'll have to write this. So this is how it works. So these things are equal, and we have shown that yesterday. And that means that you can calculate the posterior at time t two ways. Either you start from the original prior and you multiply with the complete data likelihood for every model. So that means that you multiply, let's say you have 2 days of rain, okay, or no rain. So here, instead of saying, say for 2 days, this could be the original 1/3, right? And for the first model, what would this be? For the first model, it have to be the probability of all this data, all these rainy days. The first model says here probability of rain 0.1, so that's 0.1. And the second day is 0.2, and there was no rain, so it has to be 0.1 times 0.8. So you have 0.1 times 0.8 here, and then 1/3. Now, what happens if you do it like this? Then you don't have to consider the probability of all the days here. You just look at the current day, 0.8, and your updated belief from the previous step. So this allows you to do this update recursively. Yeah. So you don't have to do the calculations from scratch. And this is useful specifically if you want to make a decision in this example about whether or not to take an umbrella outside every day. So you need to calculate the posterior every day anyway. And you don't need to have this joint probability calculated, you can just use these local probabilities. So in our implementation we'll use this. We'll use this one as the basis. And how we'll do it? Well, let's see. Here I am. Where's my mouse pointer? I can see it. Okay. So how do we work? We have this matrix of predictions for rain for every one of these models, right? And we have 3 models, okay? And we have 4 time steps, okay? Just put here number of time steps, number of models, and then here we want to, well, this is not, we don't need this line anymore. So just build the predictions, okay? And for its station of rain probability, right? So now we have a table now of 0.3, 0.4. So every one of these stations is agreeing that the rain probability increases over time, okay? Because maybe it's going to be a rainy weekend, okay? And then the actual thing happens, okay? You have rain, no rain, rain, rain. And now after this happens, you would like to say, or after every day, you would like to update your probability of each of the stations being the right station. Okay, so we'll use this formula. So first of all, this is the kind of skeleton for doing it. It will help if for every day, because for every day we only care about the predictions of every station for rain or no rain. Yeah. We don't care about the previous predictions or the past prediction or the future predictions. So here I'll use this matrix to fill in the predictions of stations. Okay, so for every model or station and for every outcome, rain or no rain, we have a probability. Okay, so that means that the columns of this have to sum to 1, right? Because for every column, for every row is a model and every column is an outcome. So for every 2 outcomes, so if you write the P matrix, it's going to be like this. Have station 1, station 2, station 3, or model 1. Model 1, model 2, model 3. And then you have rain, no rain, and then you have, let's say, 0.1 and 0.9. Yeah. And then we also have our belief. Our belief is basically the one vector of size 3, and it has to sum to 1 as well. Okay? And this is our actual observations. What did we say here? We said rain, no rain, rain, rain. Okay, so this is what actually happened, right? And now what we would like to do is to go from all days, from day 1 to day 4, and then for every model, fill in the predictions for that day. So this is just a utility function, okay? So utility loop to fill in predictions for that day. Okay, so now we have this matrix, and because the columns of that matrix have to sum to 1, then the second one of the columns is just 1 minus the other column. Yeah. Okay. So now we have to get our magic function for getting this posterior for every day. We're going to use this recursive formulation, so every day we get a new posterior, and we update it. Okay. Okay. So now I would like your help to fill in this function. So we can, instead of starting by filling in a vector or something, let's just say that this is our posterior, and we're fine. So now we know that this matrix ij for Pij is the probability of the ith models to the jth outcome, right? So we need basically to have each one of these terms in the sum. We need to calculate them. Yeah? Okay. So let's say we want to calculate one of these terms in the sum for one of the models. Okay, so for m in range, is that the right way to do it? How do we write it? N models? Yeah? Okay. So now for every model, we would like to calculate this term. Yeah. What do we write? Okay, so prior.
But you can just do it vectorized.
You can, but I don't want to.
Okay.
Let's do it with a loop.
But P, do you need to know the outcome because you calculated P as the probability of rain, didn't you? Or
Yeah, Pij is the probability of, well, j can be 0 or 1, so 0 is for no rain and 1 is for rain. And so Pij is the probability of the j thing happening according to the ith model. So for every model, I would like to get a probability specifically for this outcome. So if I'm going to do it vectorized, I have to select the column from this matrix. So if you know how to do that, you can tell me, and I can do it like this. Do you know how to do it?
well, I just put in the probabilities of rain, and then you just do. Python is really simple with vectors.
Yeah, okay. So let's do it with vectors. So we want to multiply the vector of priors, right?
You just posterior
with
equals prior times p divided by marginal, which is the sum.
okay times p, and where does the outcome go?
P is just it's a matrix of with the probabilities of rain. I just took 1 minus for the ones.
Yeah, there is one thing that we're missing here, right? So there are 3 inputs to the function. One is the prior, and one is the probabilities for different events, for different outcomes, and then there is the actual outcome, if there was rain or not rain, right? So we have to have it somewhere in there, because right now we're kind of ignoring the data. So this is the data. Yeah. So we want to include the data in this calculation. So what you could do what you say. What you say is correct. We just take P, and one column of P is when there is rain, and one is when there is no rain. Okay. So is there a way to select one column from P? Does somebody know how to do it?
You just put the column in it, and it will do the factorization.
So this is the first one. Okay, this is the row. I want to take all the rows. Does it work if I do it like this? Does it work? Is it magical?
No.
No?
You write.
Like this?
Yeah.
And then put the column in. Yeah. Inside that. First, like this column, and then,
Like this?
yeah.
Comma?
I think this.
Is that the right syntax? Okay. So this might work. Okay, let's see. So this gives us not a posterior exactly because you have not, it's not normalized, right? So so this is just each one of these terms in a vector, right? But now we have to divide by their sum. But that's easy, right? Okay, so we can call this likelihood just for, because anyway, this is basically the likelihood of every model. And then posterior should be just likelihood divided by some likelihood. Does this work?
NP or sum. NP or sum.
NP sum. Okay, so this might work. Okay. Okay, let's see. So now I have to remember how you do execution in Python. I forgot. So let me just try to remember it. Okay, exec file. It used to be a command called exec file, but now it doesn't work anymore. Now you have to use 3 different commands. Exec open read. Okay, yes, fine. Exec open and then file name posterior pi and then read. Okay, it seems to work. Okay, let's just see how it changes, right? So the one of the station that seems to predict rain most often is this one, but then here there was no rain and kind of, so we don't really know what happened, right? But what we'll probably see is that this station probability is the highest after the first day, then probably this one might become first again. I don't know. Let's see. So let's just make it print something here so we can see what happens. Okay, so just print the belief, okay? Now nothing happened. Why? I have to print, sorry. Yeah. So it's interactive. Okay, so what we see is that originally everything is the same, but then afterwards station number 3 is the highest probability, right? And then station number 2 has the highest probability, and then station number 3 becomes the best, okay? This kind of makes sense, right? Now we would like to use these models again to make predictions every day of what's the probability for rain. Now we assume that we can do this basically by doing this. This is the marginal, so we just calculate the sum again. Yeah. So that's pretty simple. Let's see. outcome probability is 0, and we'll have this code here. It seems useful. So have the likelihood for every model, and then we just sum it, basically. That's basically it. Okay.
Why do you need that get marginal function?
Oh, we'll use it later. So, how does this work? Well, let's say probability of rain. Get marginal predictive. That's what I call it, right? Belief P. Okay. So before that. Okay. Okay. So before we see anything, the stations say, okay, 0 0.1, 0 0.4, 0 0.7. So what we get is the average, right? This is 0 0.4. That's probability of rain. And then after we update, then we don't get the average anymore, but we shift our predictions according to the predictions of the average according to the belief, right? So it's not 1/3 anymore, but we weigh every station according to our probability. So this is why it's useful now, because we don't have to select a specific one station. We could do it, right? Because here we say that on the last day this station is the most accurate, so maybe we just look at this station. Yeah, that's what we call maximum posteriori, and this is a good approximation sometimes. So if everything else has a very, very small probability, like almost 0, then you just ignore it and just look at one station. But it might be that many other stations have kind of high probability, so you would like maybe to average their predictions. That's what you do here anyway. So you can use this also to make decisions. So if you want to decide whether or not to take the umbrella, you can just take an average somehow. And this is the Bayesian average. Okay? So how do you do this probability of rain stuff? Well, I think we just did it. Just the denominator of this fraction. So let's try it. Exec. Something is wrong. Theta is not defined. Not theta. Oops, something else. Missing one argument, outcome. Ah, there is no argument of outcome here, right? So we just care about rain, right? Actually, yeah. Let's make it like this. It's fine. Okay. We care about rain, so the outcome we want to predict is rain. So let's put this as an input. If you want to predict the probability of no rain, just put a 0 there. Yeah. So this should work. Prior is not defined. Did I change the name of it? Yeah, I call it belief. So let's call it belief. Okay. So the probability of rain is 0.4. That's just numerical error here. And then the second day is 65. So that's normal because we now believe the last model more than the others, right? And on the last day, previous to last day, where we kind of are uncertain between these two models, and we have very small probability for the first one, it's somewhere between 0.6 and 0.9. So it's 0.8. Yeah. So this is how you can use Bayesian inference to make predictions on average. And of course, you can use the same thing now, right? To decide whether or not you're going to take an umbrella. Yeah. So let's add to this setting, we can add a utility function. Okay. So that if a equal 1 is umbrella, a equal 0 is no umbrella, and then x1 equal rain, and x0 is no rain. Okay. Now we'd like to find the utility, expected utility of some specific action. Okay. And given all the data we have seen so far, and our belief. Okay. expected utility, you can basically write it in terms of the probability of all the models at time t, and minus 1, because you haven't seen yet the data at time t, and the probability, so you sum up all the models, and sum over all the outcomes, then the probability of every outcome given this model, okay, and then the utility of your action for this outcome. Okay. So outcomes now are rain or no rain, the same thing as before. Now you're averaging over all possible outcomes and over all possible models at the same time. And of course, for different outcomes, you have different utilities, so you have to take that into account. Yeah. So the utility function you can use here is this matrix here, let's make it like this. So 0, 1 for the action, and 0, 1 for the rain. If it rains and you don't take the umbrella, then it's very bad. If it rains and you take the umbrella, then it's okay. If you take the umbrella and it doesn't rain, it's the same. But if it doesn't rain and you don't take the umbrella, then you like it a bit. It's 1 minus 10, 0, 0. Okay? So now you would like to select the optimal action, and the optimal action is the one that maximizes expected utility according to our definition of what is optimal. Yeah, we could change the definition, but we'll say that that's what we want to do. So the first step is to calculate for every possible action the expected utility. Yeah. Okay. So let's see how you do this. So we will base this on, we will use this function here. Get expected utility belief. Okay. P, we know the next day predictions and action. Okay. We also need the U. Yeah. Okay. In this function, U, action, outcome should be the utility of the action outcome pair. Okay? Right. So now how can we do it? Let's see. We have the likelihood, right? Let's get this first. We'd like to get this for all the outcome probabilities. So we don't care about individual outcomes, let's do it for all of them. What would happen if I put a vector here as an input? Would I get a vector as an output, or would it not work? So now I can calculate this for one outcome. If I put a list of outcomes, would I get a list of outputs, or would I get something weird? We don't know. Okay, so let's just do it like this. No, let's just wait for this. I will use a for loop. Okay, for outcome in range 2. Okay, it should be an input there, but it doesn't matter. Okay, well, how do you get the number of columns for P? How do you get the number of columns for P? Yeah, the number of columns for P for a matrix.
You can write NP of shape and
Okay.
choose, I don't remember if it's the first or second.
NPP shape P2 or something like that.
I think you need the square brackets.
Okay, let's see. P will have it. Okay, NP shape
And it's
P, and we'll give you something. P. Okay.
yeah.
Okay, so we just need 1.
Yeah.
Okay, right. NP shape P1. Well, maybe I'll cut this out. and that's n outcomes. Okay, so just make it a bit more general. Utility 0 starts from 0 and range and outcomes. Okay, we don't have to consider every model individually, we just get the marginal predictive for all the models. Okay, so that's the probability of the outcome. And then utility is just U, right, of A and outcome times, yeah, sorry, outcome times P outcome. Okay, so now we're writing the sum like this. Yeah. So this is just this sum. So basically, instead of taking individually over these models, I'm summing these directly. So put this sum outside. Where is it? There it is. So swap this out. Take this sum outside here, and now this guy here, yeah, is one term. This is the marginal predicted distribution. So this is what I use. Okay, and I'm calculating individually each one of these terms in the sum, multiplying with the action. Okay. Yeah, so now this returns the utility of this action. Okay. Now, of course, you also want to have a function for getting the best action. Right? So, again, we don't really care about the outcomes anymore. And I guess that n actions is np shape u 1 as 0, right?
Supposed to do both the for loop and recursive statement.
Where?
When you get this 52. And also
Ah, so that's wrong. Yeah, get marginal predictive.
okay.
Yeah, great. Right, this is our autofill activity. That's all by default. Okay, so now we have the actions, and well, we could just put in a vector if we like, right? And get the max. Okay, and then I guess normally there is some function for finding the maximum of a vector, maximum argument. Does anybody remember how it is? Max gives you the maximum, and the second thing of the max returns you something. Let's see. X, do we have a vector somewhere? Belief, right? Is a vector. So max belief gives us the maximum, fine, but we want the maximum argument. Okay, this is something I have to look this up. Max to get argmax Python. Okay, numpy argmax. There is a numpy argmax, so let's use that. Np argmax, yeah, belief, yeah. Okay, fine. Return np argmax utility. That gives us the best action. And now we could, in theory, just select whether or not we are going to take the umbrella or not, right? There's the probability of rain. Fine. And now we can say action equal get best action. Leave P U. We haven't defined U yet. So U can be an NP matrix, as we said before, 1 minus 10, 0, 0. Okay. And we can actually plot the action that we take, as well as whether or not it rained, as well as the utility. Okay, I think this should work. Let's see. Oh, it works first time. Okay, so these are probability for rain, and here for some reason I'm seeing this complicated thing. I know it should be rain T. Okay, we take the umbrella, and well, we get 0 utility, so we always take the umbrella because we always think it's going to rain, right? As far as we can tell. So that seems fine. But here we could have gotten, on the second day when it didn't rain, we could have not taken the umbrella and it would have been better. So if our data was different, so let's say it never actually rained, right? Then we should get a different model maybe, but maybe not. So the first model, okay. So even though we're quite sure that the first model is correct, we still have a kind of high probability for rain. It's always 0.4 or something like that. Yeah. So because our utility for getting wet is very low, we still take the umbrella anyway. Yeah, we are very sensitive to rain. Right? So if we change this, then we should get something different. So let's see how much can we change it. Let's make it -1, so we're not so sensitive anymore. Okay. So now we'll never take the umbrella in this case. We don't care if we get wet so much. But if it does get more likely to be raining, then we should be getting the umbrella more often. Yeah. So the first day we don't take the umbrella, we get -1. We get rained on, then we start taking the umbrella. Then yeah. So our behavior depends basically on both what we believe about the rain and the utility function. Yeah, in a different way. So in general, setting up these decision problems is difficult for 2 reasons. The first is, what are the models you're considering in the first place? Yeah, and the prior over them, and what is the utility function that you should consider? Yeah. So in some cases it's obvious, in some cases it's not. So here we have these 3 models. We can use them. It's natural to say uniform prior over all of them, and then here we can say, well, it's objective, right? So what should you put as utility? But we have to choose something, otherwise there is no way to make a decision function. Okay. Okay. Let's take a slightly earlier break because I don't have time to go anything right now, and come in 10 minutes after 1.